Hello, and welcome to another lecture. I'm doing the second lecture on linear fractional transformation, second part of 1.4 in the book. So what we're going to talk about today is that an LFT, a linear fractional transformation function of this form, can really be viewed as a 2 by 2 complex matrix. It's really the matrix ABCD. Now, for this, we need to view the Riemann sphere in a different way. We view the Riemann sphere as the so-called one-dimensional complex projective space, CP1, or sometimes just P1. Now, the way that we define this complex projective space is we start with C2. So C cross C. A two-dimensional complex space. We take out the origin. So we take out the point 0, 0, and we define an equivalence relation on the vectors in this C2 by saying that two vectors u and v are equivalent if u is equal to lambda v for some lambda. Right? So if one of them is a scalar multiple of the other, right? And we define CP1 as the C2 minus the origin modulo this relation, right? So the set of equivalence classes given this equivalence relation. Now, CP1 is therefore what it is. It's a set of complex lines for the origin, because a complex line, you could think of, or what people call the complex line is, is basically a copy of C, right? And so what we have here is the set of all multiples of non-zero vector. Well, that's going to give you a complex line, right? So the complex line is going to be one of these equivalence classes. Equivalently, it's the set of one-dimensional vector subspaces of C2, right? And of course, these complex lines are the ones that go through the origin, right? Because the origin is in all of them. All right, now how do we denote points in CP1? Well, we're going to denote in square brackets z colon w. It's really telling you that the ratio is what's important, and that's the equivalence class of the point zw. So if I have a zw in the C2 minus 0, I denote by this square brackets z colon w as the point in the projective space, right? So that gives me a way of talking about points in the projective space. Right. So now let's identify this with the Riemann sphere. I claim that CP1 is actually the Riemann sphere, which we were writing as C sub infinity. So we define this map, and it's fairly easy to see that this really is a bijection, right? And so we define it as a map going from the Riemann sphere to CP1, and what we do is if we start with some point in C, some z in C, then we map it to the equivalence class z colon 1, right, to that point in CP1. Now notice that because z comma 1 is equivalent to any other multiple, I also get basically everything, every other point, right, on this line by multiplying by some lambda, right? So I can get anything that has the same ratio here, right? Now, the one guy that I cannot get is when the second component would be 0, because that would require multiplying something by 0, and then it's not in C2 minus 0, right? So that's the only guy that I can't get. So that's where I map infinity. Something colon 0, and because I can just factor out any lambda, non-zero lambda, this is the only such point, right? So that's where I take infinity. All right. Now, claim is that if I have an LFT like this, that it corresponds to an invertible matrix, right? A, B, C, D, right? And if you remember, an LFT is supposed to satisfy this AB is not equal to BC. And that's precisely telling you that the determinant of this matrix is non-zero. So that means that it's invertible. So that makes sense. And furthermore, if I have an invertible matrix, then what it does, well, it does take one-dimensional subspaces to one-dimensional subspaces, right? Because it's supposed to preserve dimension if it's invertible. So it does take basically, it takes points in the in CP1 to points in CP1, right? After the equivalence relation, right? So it makes sense, right? So let's see how this works. So let's look at, so we have this F, right? Let's suppose that we're in C, and we're not in, we're not the point where the denominator is zero, right? Or if C is zero, then any point in the denominator cannot be zero. So then let's look at where C takes f of z. Well, by definition, you just stick the number, stick f of z into the first component coefficient and put 1 in the next, right? Next component, right? So, okay, that's just by definition, right? Of what C is. But now this is these guys are equivalent up to any scalar multiple. So I could just multiply by CZ plus D, right? So I have this guy over here. All right. So let's also look at, well, what would happen if Z was actually minus D over C? Well, then this CZ plus D is actually 0, right? That's what that means. And so then what I'm doing is plugging in infinity, and then I'm getting 1 colon 0, and that's equal to this guy as well, because CZ plus D is 0, and so this guy is non-zero, and I can just make it 1, right? I mean, those guys are equivalent then. All right. Now, if W, so let's now go one step further. So we're gonna start in the projective space. So if W is non-zero, then Z colon W is the same as this thing, right? That's basically just by definition, right? I mean, I cannot divide by W if it's 0, but if it's not 0, yeah, those guys are the same. Now, let's look at what I get over here. So let's suppose that I plug in Z colon W into the inverse of C. So I go to the Riemann sphere, apply the LFT, and then go back to CP1, right? Let's see what that does. Well, first, what does this do? And as remember that W is not 0, and we're really looking at this point, right? So then, where does the inverse go? Well, it goes to Z over W, right? So I'm really just plugging Z over W into F and plugging that into C, right? And so, yeah, so let's just, write down what that is. We've computed that over here. It's this guy over here, right? Now, it's not quite the way I want to look at it, but what I could do is multiply it by W, right? Because these guys are all equivalent up to any scalar multiple. So I get this. But that looks precisely like what would happen if I hit a vector ZW with M, right? Oh,
by the way, before we do that, I forgot I was going to say this, right? Same thing holds if, if W is 0, right? You still get this. That's an easy thing to check, right? So it holds for any point in CP1. Sorry about that. Okay, so if I apply M to ZW, the matrix, right, I get this. I'm thinking of this as a column vector now, right? Well, if I, think of the equivalence class in the CP1, if I'm looking at CP1 corresponding to this guy, well, that's precisely this guy, right? So it takes this to this, and yeah, so it really corresponds to the map that takes a vector v to mv in C2, right? So we do get this correspondence, right? All right. So now note that that any scalar multiple of m gives the same f. It's not a one-to-one correspondence. So of course that's just like multiplying the numerator and the denominator by a constant, right? That also gives you the same f. So next, if I think of the map M just on C2, I can just think of it as a map from C2 minus the origin to C2 minus the origin because it's invertible, so it doesn't take it doesn't take anything other than the origin to the origin. So it is a map from C2 minus the origin to C2 minus the origin, right? All right, now let pi be the so-called natural projection. It's the thing that takes C2 minus 0 and gives you the corresponding equivalence class in CP1, right? And now we can write down a nice diagram that sort of that gives you how all these things are related, how the M as a map is related, how the map of the projective space is related, and how F is related, right? So we started with F, going from the Riemann sphere to Riemann sphere, and then what we did was we constructed in a previous slide, right? We looked at what this does on CP1 using this pre and post composing with this identification, right? So you went down here, then back up here, right? And we saw that actually corresponds to this matrix M, which we're thinking of as a mapping from C2 0 to C2 C2 minus 0 to C2 minus 0. So, by the way, the name commutative diagram means that no matter how you go in this picture, you're always you get to the same point. The maps are going to be the same, right? If I start over here and go down here, here, and here, I'm getting the same map as if I go down here, here, and here, or if I go here, 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 right? I start at one point, I get exactly the same point. That's what commutative means. Commutes, right? Now note that over here, these maps, well, they're not these guys are not one-to-one, right? They're, they take anything in that one-dimensional subspace and give you the corresponding point in CP1. But anyway, so this is the way to think of how all these maps are related, how the matrix and how the linear fractional is related, and it's really through this, thinking about it as a map of complex projective space. Now, one neat thing about thinking of it as a matrix is that it's really easy to invert,
right? Because you just simply invert the matrix. There's a formula for inverting a 2 by 2 matrix, right? Now, there's a 1 over the determinant. You can just ignore that because it's up to a scalar multiple. So it's actually even easier than inverting matrices, right? But it gives you an immediate inverse, right? So we definitely get that, right, over here, right? That's the that's the inverse. So it gives you immediately that LFTs are invertible and their inverse are, well, I mean, we knew that they're bijective, but their inverses are actually LFTs, right? So therefore, this is a group, right? Sometimes called the Mobius group. It's a group under composition, giving you, well, all the LFTs, right? And something that we proved last time is that this group is actually generated by translations, complex dilations, and complex inversions, right? So if I take all of those and generate the group, I get the group of all the LFTs, right? All right, now let's end the lecture on one. I don't think we really had a really explicit example of an LFT. So let's look at the Cayley map, one of the more common maps, and it's this LFT. And you can check that this is an LFT. 1 times I is not equal to minus I times 1, right? So that's good. It is an LFT. The inverse of this guy is also very, very useful. Now, why is it useful? Well, it's mostly useful because this is the map that takes the upper half plane, right? Everything with a positive imaginary part to D, to the unit disk. So it gives you a 1-to-1 relation between the upper half plane and the disk, right? And, of course, that also makes the inverse of this thing very very useful, right? That would give you, a map going from the disk to the upper half plane, right? So as I said before, the upper half plane is another version of the disk, and this is the thing that identifies them. It's the Cayley map, right? Now, why does it take the upper half plane to the unit disk? Well, this guy is in the unit disk if its modulus is less than 1, right? So, well, that's equal to, the modulus of the Cayley map is equal to this. And I can just write it in a different way, right? I just write it as z plus I, and modulus is bigger than z minus I. And then you look at a picture. What does that mean about z, right? So if z went into the unit disk, that meant that the distance to I is strictly less than the distance to minus I. Well, just a little bit of geometry, and we see that it has to be above the real axis, right? So it has to be in the upper half plane. All right, so the next section in the book is an optional section, so we won't do a lecture about it. It's about cross ratios. That's one way to define LFTs, and it's basically a quantity that's preserved, that's invariant under LFTs, and it also gives you a way of defining LFTs that do the right thing. But we won't really use it, so it's an optional section. So next lecture is going to be, we're going to move to chapter 2, and we're going to actually look at the functions that we are interested in, holomorphic functions. So that's what we're going to do next time. All right.